अभी current topic LoRa, lower rank adaptation of large language models by Edward Hu and its teams. So first we will हम लोग देखेंगे क्यों LoRa, why should we use LoRa. So it consumes less memory consumption during training, and it's lightweight deployment and no inference evaluation latency. So in adapters, in the previous papers, there are the things called adapters, which also used to uh, fine tune a model, but it caused a delay or a latency, additional latency during inferencing. We will see it in the future slides. So in the abstract, what they have mentioned is when deploying independent instance of fine-tuned model, each with 175 billion parameters, it's expensive. So on the expensive in this case, what they meant was with the RAM for the GPU memory. In case of GPU memory, uh, the billions of parameters take huge amount of GPU memory, requires huge GPU memory. We can just consider it similarly like 175 billion multiplied by 32-bit, and we can just do a twice of that number, because during training we almost have more than double of the parameters for the gradient calculation. Again, we will look into gradient calculation in future slides. Uh, So they have proposed LoRa and adaptation, or LoRa, which freezes pre-trained model weights and injects trainable rank decomposition matrix into each transformer layer architecture, which helps them to reduce trainable parameters. And one more thing that they have mentioned is LoRa
Amod,
purpose.
Amod, sorry to disturb you. Are you changing your slides? Because I don't see slides being
Oh,
changed.
sorry.
Amod, like you said,
I
like
think
hello.
yes, it got hanged. Yeah. Yes,
Uh,
Apritam, sir.
you talked about GPU consumption, right? So, are you sure, like, is it GPU consumption or is it a cost of inferring the model during
Uh,
production, after
so
production?
during product, no, after production, what I have mentioned was if we use adapters. So
Mhm.
adapter is also a technique, which also fine tuning technique, which increases the inferencing time during the production.
Mhm.
Okay, but
So, is it
what Laura has mentioned is, unlike adapters, we won't increase the time. I mean, inferencing time or the evaluation time
mm,
during the production.
okay? So, is it it is only for GPU consumption because it takes a large amount of memory? We are using LoRa.
Yes, during
Okay.
specifically during training or fine tuning,
Acha. Okay.
uh, they said that we need a large amount of memory because we have to save the gradients.
Yes.
Therefore, this what we have proposed will lessen that memory quite a bit.
Okay.
Okay.
Hi, Amod.
Yes.
Yeah, so just a quick question. Kisme jo, let's say they are saying this low rank, right? So let's say given a metric, so let's say we have this, so let's say we have like metrics of weights,
Yes.
and then let's say if we were using this this LoRa, so how does this the newer the metrics will look like?
It won't look any different from the original matrix, but it will surely have little bit of changes. Uh, I have a practical demo for that in the
Okay, cool,
future
cool, cool.
slides.
Sure,
I will let
sure.
you know at
Okay,
that time.
sure. Yeah.
Uh, okay, any other questions? Okay, let's I will go with this slide again. So in abstract, what they have mentioned is deploying fine-tuning models, each with 175 billion parameters. So let's say a GPT-3 takes 175 billion parameters, and they are saying that it's expensive during fine-tuning or training. So what exactly happens in fine-tuning or training is like we need double the parameters, more than double the parameters actually, to store in our memory. And if we multiply it by 175 billion into uh, 32 bits, and it will obviously consume a lot in lots of GB of memory. And currently we have I mean the at most I am seeing only 80 GB of GPU memory max. So therefore and quite expensive actually, unlike a CPU RAM. So going ahead, they also mentioned that low rank adaptation freezes pre-trained model weights and injects trainable rank decomposition. We will see it in future slides also. And the last point they have mentioned is LoRa performs on par or better than fine-tuning model quality on Roberta, Deberta, GPT-2, GPT-3, despite having fewer trainable parameters. So this can be a little bit debatable. So going for the next slide. So let me summarize again what the main points of the abstracts and that they have mentioned. Deploying or fine-tuning a large language model are very expensive in a typical scenario, but with LoRa, we can reduce this expense. And the second point, LoRa freezes, weights, and injects trainable rank decomposition matrix. So they are saying that LoRa will freeze the weights, the original weights of the transformer, and add a separate matrix beside it. So again, we will see this in future slides. And the third point, they are saying LoRa performs better fine tuning, which is again debatable. Okay, going for the next slide. So let's see how does a model trains. Uh, if we say here that X is my input and it's going to a model, then it should give me a Y output, a desired output. So let's say that my input is 2, and somehow I want my model to give a multiple of 5. So we know that 2 multiplied by 5 should be 10. What I desired from the model is value 10. So if someone gives the input as 3, then I want my model to calculate the value 15. Or let's say 4, then 20, 10, then 50. That's what I want from my model. This is a very, very simple model. Actually, this won't, I mean, this is just a basic model, just for theoretical purpose. So let's see how does the model train. The issue here is we have to train the model such that its weights, I mean, this weight will automatically get changed. So last time we have seen that the model, we are giving 2 here from the model, and this is a weight which is 1, and we want to desired output of 5 because we want to train our model to calculate the multiple of 5s. So when we multiply 2 multiply by 1, we are getting the value 2 again here, which is wrong. We don't want the value 2, but we want value 5. So we say it as a back propagation. We want with help of, this is just a calculation in which we changes the weights of the model. So here's what I've done here. When we give the value 2, which is here, uh, multiplied by 1, which is the weight of the matrix, we will get the output 2. This is just a forward propagation that we have done, or we can call it as inferencing or evaluation, whatever the thing. But we want value. Let's say we want value 10 or 5. Oh, sorry. We want value 10 because multiple of 2 multiplied by 5 is equal to 10. Okay. So we calculate a y gradient, which is just the output of 2 minus the what we actually want here, which is 10. We actually want 10, and the output we got is 2, and we will get the answer -8. Then we calculate the gradient of weights, or W gradient. So we will just multiply the input, which is 2, multiplied by the y gradient, which we got 8, and we will get value -16. Then we have to update the weights, this initial weight, which we had earlier. We have to update that. So we can update it using this this formula, which mentions that initial weight, which is 1, minus gradient, which is -16. And in this case, we will get answer 17. And if we do this step again from here, we will keep repeating this step again and again. Therefore, we have a parameter called as alpha, which is a hyperparameter. If we tune alpha properly, we will come to our step. Like here, we have taken alpha value as 0.25. And using this, we can get the value 5 here. So now we have updated our weights, and we are getting the value 5. So if we do a 2 multiplied by 5, we will get 10. And again, if someone tries to calculate the y gradient, so it's like 10 minus 10, which is equal to 0. And calculating the rest gradient, you will again get 0 here. And
But
again,
Amod, see
yes,
what is a gradient?
is the difference, or
So this is gradient is not the difference, right? Gradient is a derivative.
yes,
So this difference is actually the error,
yes, right.
right? And
So
then you calculate the gradient with respect to that error.
yes,
Okay, so yeah, again, maybe you can explain in that term. So this y grad is nothing, it is just the error.
error. Yes, right.
Okay, and then what do you mean by w grad?
Again, it will be the error. I mean,
But this
again,
is not the difference,
yes,
right? This is not the difference.
uh, yes, this is not a difference.
Hmm.
But
Just one question. So from where you
yes,
got these equations? You have
no,
created by
no,
yourself?
yes, yes.
No, so they are not correct.
Okay, okay. Then I will move to the next slide then.
Yeah, this is not correct. Yeah.
Okay.
Anyone else who wants to confirm that if they think that this is correct?
So, not correct. It means that it won't goes to the minimum, right?
No, no, no. So the equation itself is incorrect. See, your y is x into w, right? Your y is x into w.
Yeah.
Okay.
Yes.
Now, when you will calculate the error, so E will be equal to Y output minus Y real.
No, no, no. Y is x into w. Okay.
Now,
Yes.
Y
Got
is
it.
X into W, right? Then your
Yes.
E, the error function will be
Hmm.
the expected error minus the actual error.
Uh. Yes.
Fine. What is the expected error?
Uh. I think this is the expected error.
Whatever the number is, that whatever, like
Yes.
the 10 is your expected error. Sorry, expected output.
Yes.
Expected
Expected
output is
output is 10.
10, 10, right? And then your actual output is how much?
2.
2, or you just, if you just fill in the places, so it is actually Y cap minus X W,
Yes. Right.
where Y cap is your expected output, right?
Yes.
Into, so Y cap minus X W, that is
Okay.
your E.
Okay.
That is equal to E, right? Now,
Yes.
now the gradient with respect to W, the gradient for W would be del of E by del of W,
Yes.
right? So you take a derivative of this equation that you have written at the top.
Okay. So y cap
Y
we
cap will
already
become
is a
0.
constant.
It's a
Yes.
constant, it will become 0,
0.
right?
Minus I think
X,
this is a x
it will
into
just become
w.
X.
Yes.
It will just become X, right? So
Right.
del E by del W is minus X. Now, if you put this in the stochastic gradient equation, W new equal to W old minus alpha times into minus X.
Yes. W new equal to w old minus alpha times wx. No. How they can't be wx, right?
No, no, no,
Alpha
just
x.
X. It only alpha X will be there, right? And it is going to
Okay.
be
Yes.
plus because you already have minus X coming from this.
Yes. Correct.
Okay, so this is your equation, the update equation.
Okay. Okay.
Okay, so it is not going to update it to the actual W, the 5 in the first step. It will take multiple steps, right? So now the current value of W is 1.
Yes.
So W old is 1, right?
Yes.
Plus
Plus alpha let's say
0.25.
alpha is 2. Okay. Otherwise alpha is 2. Okay.
So alpha is 0.25 into
Yes.
X. What was X?
Is 2. No,
2.
sorry. X was 2. Yes.
So whatever the value of X, keep it that,
Yes.
right? And then
Okay.
whatever is the new W, you keep that W here, right?
Um.
Okay, so this
Yes.
equation is not
Right.
correct.
Right.
Uh,
Okay. Got it. Okay. Then I will move to the next slide. The thing I want to say in this slide was that whenever we are calculating, we need to save the x and the gradients. That's what I wanted to say. Because in each layer, we will get an output, and we need to save those output for the faster calculation. Any questions still here? Okay, then let's move to the next slide. Then, as earlier, Himanshu sir has mentioned, for the what is the I think low rank. What does the low rank means or something like that? How the matrix is different from the low rank. So they have mentioned that they have taken inspiration from this paper, which show that learned over parameterized model in fact reside on low intrinsic dimension. So what this actually means, what are the low intrinsic dimension? And they also mentioned that hypothesize that the change in weights during a model adaptation also has a low intrinsic rank. So let's look into what does they meant. So again, let's take an example. Say this is my 2D graph, and I have some
Hello.
points.
Sorry,
Yes.
Amod, like sorry to interrupt. Like
Yeah.
the gradient equations which you have showed back propagation. Overall,
Yes.
what you were telling in that equation, like you were storing gradients and like I didn't get, I missed that.
So what I was telling that we need to store these gradients for a faster calculation. So
Okay.
let's say my equation was error
Hmm.
divided by W.
Hmm.
So this is just for the single weight equation.
Hmm. Hmm. Hmm.
So in this case, we wanted to store y, which is our output. In case it will be in variable in inside the memory.
Okay.
So we can have faster calculation. So similarly, if we have multiple weight matrices in a sequence,
Hmm.
uh, so I think it will be something like this. Uh,
Okay.
this will be
I
what will
mean,
be
I
our
mean that is
activation
fine.
function.
You are overall you need to store the gradients for faster calculation, right? That's
Yes, yes.
okay. Okay.
Otherwise, we have to do forward pass again and again.
Okay. Fine. Hmm. Okay, you can carry on.
Uh, so let's say this is our 2D graph, and we have some data points uh, like this on this graph. And if we check the, I mean, the eigenvectors of here, we can somewhat see that for this graph, we will have a smaller eigenvector in the y-axis and the larger eigenvector in the x-axis.
So what do you mean by eigenvectors here?
It just show that how the variance in this graph. I mean, where is the largest variance in this graph? That's what I meant.
No, but why are you then talking about eigenvectors? You can say just about, you can simply say variance.
Okay. Uh, so then the variance in the x axis will be larger as compared to the variance in the y axis. But
Hmm.
when I will be taking SVD, uh, okay, I will say it as a variance. Okay. Variance in the x will be larger and the variance in the y will be smaller. But what happens is that when we calculate it, um, check the variance, sorry, eigenvectors, then it will scale according to the variance. Therefore, I am putting eigenvectors into here.
So there must be some equation, some algorithm, some theorem, right, that supports your claim?
Mm, no, I currently don't have that equation or theorem that supports my claim. So if I find it, I will let you know.
Okay. So, but what is your claim? Can you repeat once again?
So my claim was that higher our variance, I mean, not higher our variance. So if my variance in this scenario, if my variance is higher in the x-axis, then I will have larger eigenvector compared to the this in the y-axis. This
No,
eigenvector into the y-axis.
eigenvector larger doesn't mean anything, right? Are you talking,
Eigenvalue.
you are talking about eigenvalue, right? That's the magnitude.
Yes. Yes. But it comes with the eigenvector also, right?
No, but you do, but what do you mean by a bigger eigenvector, right? A longer eigenvector, larger eigenvector.
Mm.
What do you mean by that?
So eigenvector will be a unit vector. I mean, it. But if we multiply it by the eigenvalue, we can. It's just a magnitude.
Hmm. Okay. Okay. Fine. So at the end, you are saying that your eigenvalue on the x
Yes,
corresponding to the eigenvector, which is pointing towards the x-axis, is going to be the highest.
yes, in this scenario,
Okay.
that's what I was saying.
Hmm.
And the now going to the low intrinsic rank. Just a second. So what? So when we have SVD now, so what they have mentioned is that I have a matrix, say M, a very big matrix. They have mentioned is that the rank of, I mean, some this matrix has a very low intrinsic rank. That means, like I mentioned here, uh, the smaller eigen vector was has very low intrinsic. We can say that has nothing to do much with this graph. If we consider the larger value here, uh, let me show an example. So here we have taken the dimension as 20 and created three matrix A, B, C. Uh, both are square matrix. All the three are square matrix. Uh, and we are taking rank as 15. So this is I am going to with respect to SVD. So in SVD there is no such, I think, thing as rank. In SVD we will get three matrix U, S, and V. U and V will be an eigen vectors, and S will be the diagonal matrix of eigenvalues. So this function will convert our A matrix uh, to these three matrices. After that, I will just truncate this U, S, and V matrix. That is, I will just take the first 15 eigenvectors for the U, first 15 eigenvalues for the S, and not first, I think, sorry. Let me rephrase it. I will take the first 15 vectors for the U, first 15 diagonal values for S, and again first 15 vectors for V. Uh, so when we perform SVD on the matrix M, we will be getting three matrix. Mainly U. There will be a diagonal matrix. We are calling it as S, and there will be one more matrix which we are calling as V. Uh, any doubts still here?
Amod?
Yes.
Yeah, so like why are we choosing, let's say, rank as 15? Like, can we use, let's say, rank as 10 or let's say rank as 2?
Yes, you can take a rank as even 1 if you want, or even 0. But if you take a 0 rank, I don't think we will get any output.
Nee, let's say if we take rank as 2 and then we have this three smaller matrices V, U, V, and U, S, and V. And
Yes.
like, what are these the newer matrices right now? Like, what's the point of breaking down into three new?
So I just want to show that this matrix M, which we have got, even if we truncate some of our eigenvectors and eigenvalues, we will get the same result.
Okay.
I mean, not the same, but similar result and very close to the original matrix result.
Hmm.
That's what I wanted to show.
Okay.
Truncate eigenvectors and eigenvalues. Can you repeat once again?
Yes. So we got U matrix,
Yes.
V matrix, and S matrix. So S matrix is our eigenvalues. U and V are our eigenvectors. For the matrix, I'm just saying matrix M, but it's actually not a M. We actually multiply M multiplied by M transpose. It's actually for that.
Okay.
Okay, but let's consider is we will get the U matrix will have the eigen vectors. U and V will have the eigenvectors, and S will have the eigenvalue. So for with respect to M, S will be having square of the eigenvalues. So that means, let's say I have 25 here. Then for M, the eigenvalue of M will be root of 25, which is equal to 5. That's what we do in the SVD.
Hey, sorry, can you just tell the intuition behind SVD? We are converting from higher dimension to lower dimension, right?
No, no, no.
SVD से
We
क्या
are
कर
just
रहे हैं?
decomposing the matrix. We are just
And why we are doing that?
there is no such thing. I mean, this is not used in LoRa. This thing is not used in LoRa. Just I want to tell you what is low intrinsic rank does.
Okay.
That's it.
हाँ ठीक है, you can continue.
So let's say we take the rank 15. We got the output in A1. I will give a new matrix, say A1. So now we have truncated U, S, and V. And now we will see what's the difference between these. We first of all multiply this new matrix A1 with B, which is again random matrix, and again A also with B. And we will just check the difference between Y minus Z. And if you check here, that we are getting very less difference here. But let's try with this something with multiplying C, another random matrix, by B and subtracting it by Z. And you can see here we are getting very high difference. It's 0.9, 1 point something like that. That's what I wanted to show you. That even if I removed this U, remove these little vectors from U and UV and S and still multiplied by B, the difference we are getting is very small. I think it's in 0.06 something is the highest difference I'm able to see, or 0.07. But similarly, if you have taken a random matrix, some random matrix, and multiply it by B, and then try to find the difference, you will be getting a huge difference. I mean, they are not aligned together, we can say it as. Any questions still here?
Amod, can you scroll up again? I just wanted
Yes.
to see what are the A, B, and C matrices again.
Okay. A, B, C, and C matrix are random matrix.
Okay, and then you approximate A with a low rank matrix A1, and then you're the
Yes.
difference.
So
Okay, saying that Y and Z are almost similar. What was the non-similar part?
because because I will, if I want
No,
exactly
no,
similar.
no. I'm just asking which two matrices are not the same. You were showing, right, that for some
Yes, it's actually C multiplied by B matrix with Z. So here, this part.
C and B with Z. But
If
okay,
you want with Y, we can also do with Y.
no, I mean, this is anyways not going to be not going to be same anyways, right? Because C and B are independently initialized from A. So, ठीक है.
Yes.
Okay.
So
And can you just scroll up once again?
yes. So what I want to make that. Yeah, you can go ahead.
No, I'm clear. Okay, you can go ahead.
Okay. Any other questions? Okay, then I will go ahead. So here we can see that the matrix which we made can be a smaller. I mean, we can. There are some parts in the matrix which, even though we remove those particular information from that matrix, we are getting a similar matrix. That's what the low intrinsic rank suggests. And here, as Himanshu sir earlier told, what if I take my rank as 1? That is, I am removing too much of my information. Then we will get this very different matrix, which is very different from each other. And second
So,
thing, yeah,
while actually using LoRa, so what should be the rank, exact rank? Like वो भी कुछ hyper parameter है, like
yes,
what?
hyperparameter.
अच्छा.
That's the
Oh,
hyperparameter. We can
okay.
set any rank we
Okay.
want. Then when we perform SVD, the S matrix we get, which is an eigenvalue matrix, uh, will be in descending order. So, which mentions that if we remove this 0.04, it won't really affect our original matrix. But if we remove these higher values like 10.28, then it will hugely affect the our original matrix. Uh, so if you try to remove these higher values, then our original matrix and the newly approximate matrix will be hugely affect, because the maximum information um, is in our let's say these values.
Okay. Okay. So, acha, just one more thing. So, how are you creating this low rank matrix? Can you describe this equation once?
Yes. So this is you want a mathematical thing, or
Yes.
just
Yes. Yes. Yeah. So maybe you can just explain what is this NP dot and everything means here.
no, also wait. The mathematical equation to perform SVD, or just this NP dot what is doing?
Whatever it is written in the low rank matrix equal to whatever is on the right side. Can you explain that once?
Yes, sure. Yeah. So U, S, and V. So in
So this is clear. This is completely clear. Go to the next line and explain that. This one. Yeah. This.
I don't understand this one.
Yeah. Yeah. This one.
Okay. So we know that U the eigenvectors into U will be horizontal. Sorry, I think I have missed something here. I believe it will be vertical. So what we are doing here is we are truncating those eigenvectors. Just a second. Yes, we are just truncating those eigen vectors here. So just taking till that eigenvector. So if my u is this, okay. Let's my if my u is this, then if I kept rank as 1, oh sorry, rank as 15, then it will just take the first 15 values here. 1, 2, 3, 4, 5, 6 till here. And from this, it will just remove it.
No, but it doesn't it look like as if you are, so just write this thing. Yeah, just
Yes.
write this. Yeah.
Sorry, I have taken rank 1 in the below. Therefore, we are seeing like this.
First you write, first you output U,
Yes.
and then let us compare it with the next one.
So this is my u. I am taking the first vector of u.
Can you create a small U and V? Maybe you can create a
Uh,
small
I will
A,
create a
A keep this
fine.
as 5, right? This keep this as 5. This is okay. Right. And then rank you can keep 3.
Okay.
Fine. Yeah, again change this rank to 3. Okay. Now yes. So U is, this is your U.
Yes.
Okay. Okay, fine.
And similarly for v.
No, U is okay. Wait. Just keep it as U. Right.
Okay.
Now run the next cell. This one. You run
For the s1.
24. 24 has been executed. I just
Yes.
want to
Yes.
compare 23 and 24.
Both have been executed.
So see, uh, it is taking all the column, it is taking all the rows and restricting first 3 columns.
Yes.
That is what is the first thing. Now for V, it is doing what? Just go to the V.
Yes. I might mess with the u and v, I believe.
And
I
then
need to.
V is kind of, yes, it is, yeah, so it is kind of taking the first 3 rows and all the columns.
Yes.
That's what it is doing, right?
Yes.
First,
Right.
first 3 rows and all the columns. Okay. Now, what is the middle one?
That's s. It will give us output in array form, 1D array. So it's just a diagonal matrix. So it won't give us diagonal matrix, otherwise it
That
will
is
be waste
okay.
of space.
Just no, execute. Yes, execute S. Okay.
So
Amod, S is not a diagonal. It's the values. It's a vector.
yes, because if they write it here as a diagonal matrix, then it will just waste our spaces.
Hmm.
So they have
Hmm.
just given it in an array format. The function here,
So
sorry,
now
the
tell me what is this exact thing doing? NP dot U comma NP dot this thing comma V dot V this entire thing. What is this equation?
it's multiplying. Just multiplying s with v, then multiply u with the result of this. That's it. So we can get this same result here also. If I let's what should I call this matrix as
Hmm.
u1 maybe. Let's display u1. One here also same. And S1. Maybe I should take a integer values for easier representation. So we can just multiply this with V1. And if we multiply this whole with U1, we will again get, I think it is getting confused with
You have to
this.
convert S1 into a matrix, a diagonal matrix, right? That you have not done here.
Yes,
Okay, fine. Okay, so you are creating this low, but that is known, right? So what is so special here?
that was not known to me at least.
No, but this is not something which is a kind of a very good, very big contribution. So it is known. Like you don't know it, that's a different thing, but in general, this is known.
Yes, this is known. This is what they haven't mentioned it.
Okay, so what
That's I have
have they
mentioned
done
it.
after this, after creating this low intrinsic dimension?
No, they haven't done anything like that. They haven't done anything like this. I'm just explaining why this low intrinsic rank they have mentioned so much in the paper. If we see it, they have mentioned every time low intrinsic rank everywhere.
Okay.
So
Okay.
what does it actually means? That therefore I just go through and just saw it.
Fine. Okay, now can you go to the presentation once? This is
Yes.
clear, right? Hmm. Hmm.
Okay. So I will continue. Okay, there are different ways to fine tune the model. Then there will be first adapt using adapters. Then fine the simple fine tuning where we just perform the fine tune on the whole weights, taking the all the weights. So let's say this is my first layer, this is my last layer, this is my first layer, and here is my X. So whatever weights we are taking here, we will take this whole weights and calculate its gradient and store it in the fine tuning method. And they have mentioned the prefix tuning also that I haven't gone through it. But in adapters, what I have seen is they add a layer here uh, of some layer. I mean, add some adapter layer having a matrix here, and they just multiply it. And when in during the fine tuning, and after that, this adapter layer will be still here even after the fine tuning is completed. If we want to evaluate or do some inferencing, we have to go through these adapter layers also. uh, that's why they have told that these things takes latency, extra time to go through. So now I will talk about what they have done uh, in LoRA. So first of all, they have we have our X as an input matrix. Normally, our X will, if I have a X, it will go through these pretrained bits and it will give us output, which here they have mentioned is as H. Sometimes we mention it as X dash. Uh, that's the normal case. Here they have said we will take two extra matrix named as A and B. So this is A and this is B. And we will have B matrix a zero matrix, the null matrix, and A can be randomly initialized so that whatever we get here. So when B is zero matrix, the whole equation will cancel out and we will get the original value itself, which is Wx, which we wanted. This is during inferencing. So initially, this is not affecting uh, our original model in the initial case without any training. So during training, they sent X to pretend weights and X to A and B matrix. And here they have mentioned that our pretend weights, which we will call it as W, are frozen. That is, we won't calculate the gradients for these weights. So here in this case, what regular fine tuning does, it will, and this W dash is a change in, these are the gradients which are stored here. That's what they mentioned. So they have, they said that we can just convert this matrix into a B and A matrix, which are of low rank. So they have said that B and A can be D cross R and other can be R cross G, which after multiplication, we will get D cross G, which is the dimension of the original matrix. But this will store very less amount of data, but all the data will be of will contain majority of the instruction, majority of the information. That's what they have mentioned.
Amod,
Yes.
have they specified which factorization technique they have used to like decompose this uh, delta D, delta W, the gradient matrix into B and A?
So they haven't used any techniques to decompose it. They are initializing new matrix B and A.
Oh, so we will just initialize a matrix A with a rank some R and then is it like that?
Yes. Yes, right.
Oh, and
So
then we'll train
A
to
will be a new
find the
matrix.
exact A and B matrices.
Yes. A and
Okay.
B will be a new matrices. Yes,
Okay.
go ahead.
Okay.
Okay.
So just
Uh,
one clarification here, Amod. So whenever we are, anyway, we don't have to do anything at the time of pre-training, right? So at the time of fine tuning, we will keep W0 as fixed because these are the pre-trained weights, but we will update our A matrices, right? The weights
no,
which are there in the A
both
matrix.
both A and B.
A and B. Okay. So B in the beginning will be 0.
Yes, because we don't want to change our original matrix, original model. That's what they are saying.
Okay. Okay. So that means at the time of pre-training also we had B only, right?
Uh,
Well,
no,
like the
no.
B as a null
During fine tuning, we have a B as a null
in the beginning, or
in the
like
beginning, initializing. While initializing the matrix.
at the time when we initialize, it is B, and then A is sampled from this normal distribution,
Yes,
which will, but it is a trainable, right? Initially, it is random.
both are trainable. Both are
Both are
trainable.
trainable.
Yes, they have choose. We can choose A as null also. That's not the issue. Uh, why we want one of these matrix to be null here? Just one of these matrix to be null. So whenever we are doing forward pass during the fine tuning, uh,
Sir, one more question. So,
yes,
यहाँ पे we are saying that we'll, so in A we say that we'll initialize it with Gaussian values in 0 to sigma square range, right? And the rank should be R. But what is the
yes.
actual dimension of A?
Actual dimension of A is D cross R in this photo, in this image.
Okay. Okay.
So when we multiply here X, we will X, which is maybe 1 cross G,
Got it.
we will get 1 cross R. So thing here is we want any one of these matrix to be 0. So during the forward pass, these weights, these randomly initialized weights should not affect the output. That's what, that's why they have kept one of this matrix 0. Okay.
No, I think the reason to have a null matrix is because we want to sort of approximate these values, right? Because otherwise then it would be the same amount of computation, right? So
No. Reason to have null values, if say these values are not null and I am doing forward pass here, I multiply x by this. So originally what in the forward pass, what I want is my original matrix output. That's what I want. So let's say my W is 2, my X is 1. So X is equal to 1 and W is 2. Then I should get value 2 initially. But if I kept some values here, let's say both B and A multiplied, we are getting value 5. And I'm doing forward pass initially. In the first stage of the fine tuning, I'm doing the forward pass. Then I will get value 12, which is totally different from my original model. Therefore, they are said that let's keep B as 0. So if I keep B 0, it will be 0 and even though if we multiply by x, we will get again 0. The
okay.
original value will be maintained.
Okay, maybe you can explain the next step because then it would be more clear. I understood
Yes.
why you are saying that B should be 0.
So I
Maybe.
think the idea here is that if suppose we have a pre-trained model, then until and unless we do not fine tune it, it should give the same result.
Yes, correct. That's exactly what they have mentioned.
Right. Because if I suppose update all these weights and I add this B and A randomly, then the actual outcome of the pre-trained model will change, which they don't want
Yes,
to change.
right.
Right. Because we have not yet done any kind of a fine tuning.
Yes. That's exactly what I meant. Okay. Uh, Going forward, so when we get this is, let's say, a single layer. I'm for saying first layer, let's say. Mm, X will go through the pretend widths, which they have mentioned in this equation. And again, X will also go through A matrix. It will multiply with A matrix first, then it will multiply with B matrix, and then it will, and then both of these values will be added and give us the value H, which is our output of this, let's say, some layer. Or and here we are keeping the pretend weights as I mean, we won't calculate the gradients from these pretend weights. So during backward propagation, we will just update B weights for B matrix and A matrix only. That's it. That's what they have mentioned in the paper. So the gradients for these pretend weights won't be there. So we are saving dx d square parameters here. We are saving d square parameters, not actually d square parameters, like something uh, d square minus something like that, 4 RDs, I think. Yes, d square minus 4 RD parameters we are saving here, which will be a lot if we take the value of R very less than D. So in paper, they have taken values of R as 864, and D will be 1K or maybe 512, which is very less, and it will save lots of parameters.
So
That's
can
the
you
crux.
just 1 second? So how come this 4 RD has come?
Sorry, 2 RD. I mean 2 RD. Sorry, my mistake.
Okay, and so what could be one value of D and what could be one value of R?
So one value of D can be 512, and R we can take 64 also. R is a hyperparameter. We can take any value. but let's take 64 for the safer purpose. And let me
Okay.
calculate these values. So 500 multiplied by 500, we will get 250K. And I have taken 60 for R here for the easier calculation. Again, 500 multiplied by 2, we will get 60K here. And if you subtract it, it will around, I think, 190K. We are saving 190K parameters here. Okay. Any doubts still here? Is this, I mean, the diagram clear? I mean, how the fine tuning for the LoRa works and all this thing.
Oh yeah, this at least to me looks okay. But where is this low rank adaptation here?
These two matrices are the low rank.
But they are actually not ranked matrices, right? They are just some randomly initialized small matrices.
Yes, but if we see that we are multiply it with a small matrix.
Mhm.
Uh,
No, my question is the following. See, when you do SVD, okay,
hmm,
you can regenerate the original matrix with a very small error.
yes,
That's how SVD was proposed, right? Now,
yes.
now here, have they given any proof which says that if I multiply A and B and with maybe some diagonal, some other scalar value, then we
Hmm.
are going to regenerate that delta W matrix?
No, they haven't given such thing that we can regenerate delta W matrix. They are just saying that this is a fine tuning technique which will n- fine tune the model for sure, but
Mhm.
it will take less memory. They are mentioning less memory.
No, that is
So
completely fine, but they are relating it with the rank, right? So these are not low ranked matrices, I would say, as per
uh,
se.
yes, they cannot. I mean, they haven't proved that these are low rank metrics. What they have said that whenever we are our weights in our model are low rank, that's they have. I mean, that's the statement they have given from the earlier paper. So let's me go to this slide. We take inspiration from Lee and this paper. We show learn that overparameterized model in fact reside on low intrinsic dimension. So they have just assume they haven't they assume that each I mean every time the weights will be low rank. So this delta W will be low rank when we calculate it for a normal fine tuning. That's
Fine.
what they assume.
Okay, okay.
They
ठीक.
haven't proved it that this is 100% low rank or always be low rank as such.
Okay, sure. Thanks.
Okay. So no any questions here for the other audience member? Okay, let's go ahead then. Uh, so here they have shown us that we have done on these two data set, PKSQL and multi-NLI matched. Here they have done for the fine tuning. For the fine tuning, the number of trainable parameters are 11. It's in log 10 scales again, and the validation accuracy is quite similar to what the LoRa here mentioned. And that's what they have shown here again. And yes, and they have taken different values of K, and hence you are seeing different triangles there going forward. They in this paper they have only worked on self-attention layer, that is QKV matrix and O matrix. They haven't done on feed forward network on any other layer. So what I observed from in the past, that we can have low rank for the self attention, but we cannot have that much low rank which we take for the feed forward network. Otherwise, the output will degrade a lot. So here they have tried with different ranks, rank as 8, 4, and 2, and then 64. And in future paper also they have taken rank 64. They haven't took a rank as 1, 2, or 4. And they have mentioned that performing LoRa on Q and V matrix is far better than performing on only Q matrix or Q and K matrix uh, in the paper. So this on the in the self attention, they are getting good result for these two, performing LoRa on Q and V matrix and Q, K, V, and O matrix together. So any questions? Okay, we'll move on.
Acha, just one question here. So not on the K matrix, WK?
They have done on WK, but they told that we are not getting as good result as QV. Sorry, they have done on QK, but they aren't getting as good result as QV.
So the results are not, I would say the results are not um,
For their
better
case.
better than the actual fine tuning, right? They are
Ye-
talking about the decay in the result, right? So decay is not much as
No,
what you see, or the results are also better.
no, they are what they are saying that so LoRa gives us option where you want to do, I mean, where you in on which weight you want to attach LoRa. I mean, attach the AB weights. So we can attach on query weights, value weights, key weight, on the key weights, on any other weights, we can attach these AB weights, I mean LoRa weights or adapters. LoRa gives us that option. So they have further explored that which weight should we apply this, like if I do fine tuning only for the query weights, how will be the result? Then for only key weights or together Q and K weights, then how will be the result? They have
Sir,
just shown here.
sir, they have showed LoRa performs better in the previous slide. Can you go back to the previous slide? So
They have
here,
shown.
so yeah, so
So
it is performing far better. It is like 0.291 for fine tuning, and this LoRa is 2 points better performance with LoRa.
so the thing is that I
Yes, at
mean,
least in the Wiki SQL, it is comparable.
Yes.
Multi-API, it is better, right?
Mm.
Which is bit surprising, actually.
and they can do cheating in the publishing paper. I mean,
That's not,
they have to publish paper.
should not say
And
this
the
thing
last,
publicly. Yeah.
yes, I should not say this, but in the future paper, some paper mentioned that LoRa is not doing good and all those things. So we don't know. That's the thing. Therefore, I haven't said that LoRa performs better than
नहीं
on fine tuning.
ये paper like who are the authors, like which affiliation?
That I haven't checked.
Okay,
It's
fine.
the only paper that you have given to me, the archive paper.
अच्छा okay.
In that paper, they have mentioned that LoRa does not do good only with coding and mathematical data set.
Right.
That they
That
specifically
is the
mentioned.
newly published paper, right? Okay.
Yes.
Mhm.
Therefore, I'm not saying that LoRa is doing better than fine tuning all those things. I'm just saying that LoRa will reduce the memory utilization. Okay. So why LoRa? So we know we have seen that less memory consumption due to A and B matrix. Then lightweight deployment. So what does the lightweight deployment mean? So generally, when we do inference, when we do fine tuning, we store the whole matrix, whole all the matrix here, all the parameters of our model, we will store it. So if my model is 7 billion, then we will store all the 7 billion parameters. So what LoRa says, no need to store 7 billion parameters. Just store the A and B matrix and some mapping. So if my A and B matrix is of 1 billion, then we will just store 1 billion. So if we are doing multiple fine tunings, let's say I want a chatbot for this specific domain, for domain of education, then health domain, but my base pre-trained matrix is the same. So my base pre-trained matrix is of 7 billion, and I will have 1 billion for chatbot of domain in health, and then another billion of weights for the domain in education. So in case you want to inference this matrix, sorry, inference this model, the education model, you just have to take the pre-trained model, the base model, and add this 1 billion matrix to this base model, and you will get that model. In normal scenario, in the classical fine tuning, we have to store these 7 billion, which will give us, I think, 14 billion of storage space. It will just wait, utilize this 14 billion of storage space. So that's why they are telling that it's good for the lightweight deployment, and hence we during fine tuning we are seeing that only adapters weights are getting saved. So they have features to add those adapter weights and get the original, I mean the education, fine tune on education domain model. And again, they have said that it does not add latency like adapters. So
Amod, just one
hmm,
question here. So, see, I have not seen adapter. So, can you give me some idea if you know what adapter is and how they introduce latency?
okay, so I just have idea of adapters. What they have shown, I mean, given is that this is my layer one, not layer one actually. So this is my layer one. This is my maybe a self attention layer. This is feed forward network, and I will just add an another matrix, just an another layer which will have a linear matrix. So the output of this will be multiplied with this matrix. So that's what they have mentioned, and this matrix will be kept here even after the fine tuning. I mean, during inferencing, this matrix will be here. That's what the adapters they have. I mean, I have seen. So they just add one more layer for each. They just add one more sub layer for each layers of our model.
Okay. And how was it introducing this latency? That is not clear to me.
So actually, the latency they are introducing is will be in milliseconds. I mean, it's not the huge latency, but it's still worry us a little bit. So when when this matrix will be trained, fully trained, uh, this will be uh, kept as it is during inferencing also. So we are just getting extra parameters during inferencing.
No, but you
That's
have extra parameters for this LoRa also, right?
no,
Those
not
A and
during
B.
inferencing. So not during inferencing.
No,
So
suppose
what
you have
they
done,
have
no,
done.
no, listen. Suppose you have the pre-trained model, you have fine-tuned on it, and then you are inferencing from this fine-tuned model.
Yes. So what that old weights, I mean pre-10 weights, I will calling as old weights,
Hmm.
will be equal. The new weights will be equal to the old weight plus A and B. So we just have to multiply A and B and add it to the old weights. That's it. And we will get the new weights of the same dimension as old weights. So no extra parameters during fine tuning. So during inferencing or evaluation.
I think, Amod, these are still extra parameters, but probably this is parallelizable. So we don't have a dependency between the W and the AB matrices. Probably,
No, no, no.
I mean, I'm not
Uh,
sure, but I'm asking.
So you might see here as an extra parameter during fine tuning. Yes, during fine tuning, these are the extra parameters.
Hmm.
And uh, so
But
technically, yeah,
right, when
yes,
we
go
are,
ahead.
will we keep
So,
while we are
mm,
inferencing?
so when we have to do inferencing, we can just this. Oh, sorry. This is a this is a matrix. We can do it like this, can't we? Uh, X is a matrix, A and B are matrix, W or
Uh-huh.
not is matrix.
Right. So
So
it is still extra parameters, right? Because even initially अगर हम नहीं करते तो we would just have one matrix which is W. So but the only part is I think probably is that this is parallelizable. So we can do separately WX plus ABX, right?
no, these are still not extra parameters because if we will multiply B and A, we will get some output. Let's say we will get C. Then we will add C with W0 during initializing our model. This is during initializing our model.
Okay, but okay, and now I understand. So that means when your model has been fine-tuned, then you will just remove A and B, right? And you
Yes,
will add their results directly into the W0.
yes.
Okay.
So if let's say our model has completely fine-tuned, A and B matrix are fixed. Yeah, we are satisfied with our A and B matrix. So we will just multiply A and B matrix, we'll get C matrix. Then we will add the C matrix with W naught matrix. We will get W new matrix. And we will just keep replace these pretrained weights with W new matrix. I hope this is clear, Didi.
हाँ, got it. Thanks. This makes sense.
Now, there is one problem here. So go to the next slide then.
Uh,
Not this one. There was. So suppose now you are going to use the same pre-trained model for multiple tasks, right? For
yes,
each task, your A and B is going to be different,
yes.
right? Now the thing is, ki, how are you going to combine those A and B with their actual pre-trained? Because then you cannot generalize it for different tasks.
Uh, no, I don't understand your question. Can you please repeat?
Yeah, so suppose now you have one pre-trained model, right? And suppose the same model is going to be used for three downstream tasks.
Yes.
Now for each downstream task, you will have three triplets, A, B, A, B, A, B,
Okay. 3D plus AB. Okay.
right? So your base model is a single pre-trained model.
Yes.
And on top of that, you have three different A-B matrices,
Yes.
right? Now you have fine-tuned it, everything is fine. Now suppose you are passing some instances.
Hmm.
Okay. So one time you have to use it for downstream task one, one time you have to use it for downstream task two, one time you have to use the same pre-trained model for downstream task three.
Hmm.
Okay, in that case, you cannot kind of pre-compute AB and add it to the pre-trained weights of W0.
And then we have to, there will be a latency for computing this weight matrices for this our main model. So if you are thinking like in my there is only one GPU and I want to run all the three models one after another, right?
Hmm.
But if we check in the normal scenario, we cannot run three models in a three different models in a single GPU due to the memory issue. That's the first scenario. So we need three GPUs for that. So secondly, going with your scenario, let's say I have computed A and B with W. That's what my speculation is. Let's say I have computed. We just add A and B for this first task. Then we just have to subtract this A and B and add this another A and B here. But what in the paper they have mentioned is not something like this, but something like we are saving our storage space. Simply in a putting in a simple word, we are saving our storage space while initializing a model. say I need to initialize here 7 billion in
That I
CUDA 1.
agree. That I agree, but I don't agree on this adapter. See, adapters were also created for the similar idea that you have a single pre-trained model and then you have adopt it for multiple tasks, right? Yep.
Okay, this adapter.
Right, right. So latency wise,
Uh,
maybe just look for this thing, right? Why?
this adapter is right. We can have that multiple models for this adapters.
Okay, fine.
They are just telling this for fine tuning, the normal fine tuning that we are doing. So in the normal fine tuning, we just change the original weights itself.
Fine, fine. Okay, okay.
So I so any questions still here? Though LoRa is completed, I believe. Yes. Okay, I will quickly go through QLoRa. So QLoRa has given I mean invented three different things. The first one is 4-bit normal float, which is just a theoretical side. And then they have said that we have invented double quantization, and then we have given core for page optimizer to manage memory spikes. So this page optimizer to manage memory spike is just transferring pages from GPU RAM to CPU RAM. And they have given bits and bytes code to quantize the model. So what are the data types available for us? So FP32, FP16. Then we have
What is
what?
a quantized model?
I will come to it. So there are different data types we have. FP32, FP16, TF32, and BF16. Sorry, BFloat 16. So BFloat 16 is also called as BrainFloat 16, of course made by a Google Brain team. Um, so why they have invented these extra weights? Just for easier conversion from FP32 to somewhat smaller range. So here what they are doing is just if someone wants to convert FP32 uh, FP32 to BF16, they're just truncating this part of our precision and just keeping the rest as same as it is. This is similar, I mean, very close to it, not exactly what um, it really means. So uh, there are two quantization techniques. So normally how we quantize how can we quantize the thing here? Just a second. So let's say I have a value 3.146. If and I'm converting it to integer 3, that's it. We are removing these 146 values, just truncating it. I mean, just destroying these values. We can call this as a quantization. But in our deep learning or in NLP tasks, this is not good. We cannot directly, what we say, directly truncate a decimal value because all the calculation we are doing is on decimal value itself. Uh, yes. So now they have added two. So there are two quantization techniques: ZPQ and absolute max quantization. So first we will check what is ZPQ. See, let me take an example. I have a floating point from -1 to 1, just a 32-bit floating point number from -1 to 1. And I want to convert it to a smaller number, let's say in 8-bit of integer. 8-bit of integer, which is going from minus 127 to plus 127. And this is an 8-bit of integer. So what 0-point quantization is saying is, if we want to convert this, then we can just let's say my 32-bit number is 0.3. We have to multiply this with an 127, which is the higher bit of this integer. 127. All the numbers of our 32-bit, we have to multiply with higher value of our integer. And whatever the value we are getting, say I believe it is 38.8, we will just round it off to 38 then. Oh, sorry, let's say 38.2, then we will just round it off to 38. That's what the integer point quantization is saying, but that's not the optimal way to quantize our model, and that's not what QLoRA has used. So we will go with ABS mass quantization. Let's say we have a vector or a matrix having 1.2 or 5.4 and maybe 3.1 and so on. These are our vectors. Now we have to quantize this matrix. So absolute max quantization says that we first need to get the quantization constant. So let's say QC as a quantization constant, and we will divide all the values. Sorry, get the maximum values from this vector. So currently the maximum value is 5.4. We are getting 5.4, the maximum value from this vector. And whatever the value we are getting, the output we are getting will be our quantization constant. In this case, it's 23.5. And we will then multiply this 23.5 with all the vectors here. And then rest as the 0-point quantization. When we multiply all the vectors with the 23.5, then it will round off to nearest integer values. What it will do is the high, whatever we are getting, yes, it will, I mean, how does it, what if work is like this? Let's say I have 2-bit, maybe 0, -1, 1, 2. If I want to, it will just fit these values in each of these values in these packages. That's what they will this will do. So for example, 0.3 will be here, not here. 5.4 will be here. 0.3 will be here, and other values will be here. Those are which are negative values will be in this area. So let's say -1.1, or and here we can say 0.01 will be all those values will be here. That's what absolute quantization is, how the absolute quantization works, and that's what they have used in QLoRA. So any questions still here?
Amod, like
Yes.
after you are multiplying all this 1 to 5.4 with 23.5, what are you doing?
No, that's the we are rounding off. That's it. After multiplying this by 23.5, we will round off the value to the nearest integer. That's the mathematical equation. what I was telling in this package form, that I was just explaining how it's exactly quantizing. It's actually not quantizing, just putting each and every value in its bit each packages. So let's say our integer is a 2 bit. We have 2 bit value. We know that 2 bit value will have four let's say, so 2 bit value will have 0 0 0 1 1 0 1 1 like this. So we can assign this whatever the numbers we get to here in this area. That's what I was talking about. So for you here. So I hope you are getting it.
Yeah.
So that's how that they are working. I mean doing. So again, how QLoRA works? It applies quantization on the frozen pretense weights. So QLoRA applies quantization on frozen weights. So it's LoRA, just addition extension of LoRA, the extra plugin for the LoRA. So we have seen in LoRA, these are weights, my A matrix, my B matrix. So this W matrix is our frozen matrix in LoRA. Is our frozen. The weights won't be updated in the W matrix. So QLoRA applies quantization on this specific W matrix. So it converts this.
Amol, sorry to interrupt, but the quantization of this, is it on the weights or the gradients?
Weights.
I think you pull down the gradients and then you perform this operation and then तुम फिर से let's say तुम dequantized वाले weights को like gradients को फिर से update करते हो main weights में.
नहीं, यहाँ पे उन लोग ने स्पेसिफिकली मेंशन किया है कि it applies quantization on frozen pretense weights. We will check the paper later. Okay, in the last of the slide, I will go and check the paper. Okay.
Your voice
so
is bit low.
okay, sorry. It's clear now, or it's still low?
Yes, it's fine.
Okay. So we will in the end of this slide, we will go to the paper and check if it clearly does on pretense weights or the gradients. So it actually does on the pretense weights. It will quantize it to 8 bits. And when the weights are needed for the back propagation, they are dequantized again. So it won't, LoRa won't calculate the gradient for these weights, but it needs this weight for the calculation of the gradients of some another weights which are in the lower layers. Therefore, it has to dequantize these weights. So now when so you can view the quantization as, let's say I have numbers and we are keeping the numbers in some boxes. These are 4 boxes. We are keeping those number in these boxes. But the weight matrix which we have is of, let's say, 1k of 1k. Then even though we have taken 8 bit of integer, we have 256 box, and we cannot fit all those values 1k into 1k values in 256 box. So what they done is that they are making small blocks. They are making small box, and each box will be assigned with a QC, and quantization constant. Each box will be assigned with a quantization constant, and for each block it will be storing different, we can view, we can imagine it as a different boxes. So number of if we have say 5 blocks, then it will, and if say if we want to convert to 8 bit int, And if we have 6 boxes, then we have 6 into 256 number of boxes to store. So each block, so this block will be storing on this particular 256 boxes. This block will be storing in another 256 boxes. Like this, we can view this quantization as. Any questions still here? Okay, moving to the next slide. That's what the double quantization is. Sorry, double quantization. That's what what I mean by dividing tensor into smaller block and quantize each block separately. So in double quantization, we are dividing this tensor into smaller blocks and having quantization 8-bit of integers for each blocks. These 8-bit of integers will also create a huge what say will also make a contribution to a huge parameters. So again we are quantizing this 8-bit of integer, that is the quantization constant QC. Again we are quantizing these 8 bits in further quantize we are doing further quantization for this quantization constant. This is what they meant by double quantization. And then page optimizer, it's just they have given a code for which transfers between CPU RAM and GPU RAM when needed, hence preventing out of memory during training. That's it. So any questions?
Amod, so like just to iterate, ki, let's say if you're talking about low interesting rank, right?
Yes.
In let's say in LoRa. So like how do we define this rank? Like can you just repeat it again? Like it
It's just
is
a R matrix.
hyperparameter, right?
Yes, it's just a hyperparameter.
But I was just wondering, let's say if we have this eigenvalues, and then using this eigenvalues, we found out like the in our eigenvectors, or let's say the weights which we have. So if we take the maximum value, or let's say we perform some computation, and then we choose like empirically, or let's say we choose the newer weights, like given
Yes,
these eigenvalues and then
yes,
our eigenvector. So that will make more sense rather than just using, let's say, using this R as a hyperparameter.
yes, right. But during fine tuning, someone has to sit on the computer and just check which is the highest eigenvalue, because it is relative. Whatever the eigenvalues
So
are,
we can write a script for that, right? Keep
yeah,
like
we
choosing the
can write a
I.
script. But let's say all the eigenvalues are 10, then we have to add that specific thing in the script also.
Those cases can be handled, I think.
Yes, those cases can be handled, and a new script need to be made for that.
Like, is there any paper doing such kind of thing? Like,
I don't.
where we have this, let's say,
Yes,
automatic kind of, let's say, LoRa, like this.
yes. We don't have such paper, but we cannot do this with what we say LoRa, because LoRa does not do SVD. So it directly has two matrices, which they are calling low rank matrices,
Mhm.
and they are just getting the numbers. I mean, back from the back propagation, they are just updating the numbers on those matrices. So we cannot get the which eigenvalues are small and all those things. But this SBD will help this specific thing that we have that I have written code for. This will help for I believe for adversarial network also, maybe.
Mm.
Maybe. So anyway, they have mentioned in the paper for the LoRa that it helps for the adversarial network. Sorry, adversarial attack. But they haven't given any such further explanation why does it help for adversarial attack. So this is my speculation that it does not take the detailed information of each of the matrix. That's what I think. So I
Adversarial
hope
could
this
be
is clear.
yeah, the reason for adversarial could be, let's say, if we have this weights and then we are performing some operation. So anyways, the information is still there, and if we are doing some operation, so like whatever information was earlier present, that we can deviate to something else.
Oh, yes, it
Yeah.
might be that.
Okay.
So do we have time? I don't think. Let so any other questions, or anyone want to see this code, or let it be?
Amol, I am just wondering ki, I mean,
Yes.
so I could be wrong. I'm just trying to think, and maybe you can correct because you have read the paper. So maybe one reason we don't do SVD and actually train these A and B matrices is maybe because we don't know. I mean, we don't have a fixed matrix, right? Because whenever we are seeing the fine tuning data for every batch, we'll have a different delta W, right? So
Yes, right. So this SVD just for the information, what are the low rank metrics? I mean, how are our this highest eigenvalue is consisting the more information as compared to the lowest eigenvalue. Even if we remove the lowest, that is 0.04 eigenvalue, it just won't affect our matrix. So
हाँ,
they have
SVD में तो the concept is only that कि if we have a low rank matrix, for example, then the number of non-zero values in this S would actually be the rank of the matrix. So if by default like the matrix is low rank, then by default will have only some k number of values because the rank is k. And then k rank में से भी we can actually ignore say some n and only pick some m eigenvalues which actually have the most influence, and that can be used to approximate the matrix. But maybe I'm just trying to understand कि maybe we don't apply SVD directly to learn these A and B type ka matrices. And
yes. And on top of that, we cannot. I mean, in LoRa, they have uh, decomposed that matrix.
also SVD may this I'm not sure, but maybe SVD can only be applied to a square matrix, right?
No, it can apply to any matrix. So there was another decomposition. I don't remember it. But SVD can apply to the any matrix. What we do is the original matrix we have, we
Mhm.
just
Oh,
multiply
we
it,
create it and create a
m multiply by
right.
m multiply by m transpose.
Right.
So
हाँ, तो we
we just
convert
multiply
it
the
to a
original
square
matrix.
matrix. Mhm.
So this will be the Z matrix, or let's say the A matrix. Yeah, Z matrix बोल देते हैं इसको.
हाँ,
So
and
this will automatically creates the square matrix for us
then
in
right.
SVD.
Mhm. ठीक है, okay, thanks.
And now for the scale, just a second. What and we can see here is our method QLoRA uses novel high precision technique to quantize the pre-trained models to 4-bit, and इसने mention किया. Okay, that's it. Any other questions?
No, are you covering DORA? Like you can move to the next presentation.
We don't have time. I mean,
Okay.
I haven't prepared it also.
Oh, but DORA is like domain adaptation something, right? Using
नहीं
DOM.
नहीं वो decomposition है.
Okay.
It's like just they are saying कि we can decompose the original matrix and just train it directly instead of A and B.
Oh,
So
so how are we doing that?
that I need to check.
But okay, that is a lot of computation, right? How are we going to decompose the original matrix?
No, actually they aren't decomposing it. Just similar to LoRa, they're just updating some of the parameters. So there is a magnitude parameter, then there is a direction parameters. They are just updating it. But
Okay.
the way they have explained is like we are decomposing the matrix into a magnitude and direction, and according to that we will update those parameters, something like that. But I haven't read the paper to the fullest. That's what I got from the go through the paper.
Okay.
Maybe some next time I will explain to Dora.
Okay.
Uh, so are there any questions? And in SVD, if anyone have to do SVD, then they just have to um, define the matrix. Let's say LoRA for the query matrix, LoRA A, and just randomize this matrix and make another matrix as B.
Or
And
one
then
other thing is like SVD itself takes a lot of time, right? अगर larger matrix को अगर हम करना चाहे तो it takes some good amount of time.
yes, SVD takes lots of time because it needs
Hmm.
to go through the
Yeah.
back
Hmm.
propagation for A and B, as well as the preterm values also, preterm weights also, for
Yes.
both of these. But if you are going to save the SVD matrix, it will be saved faster
Hmm.
because they are only saving A and B. So for each step, during fine tuning each step, you are saving on the original this using LoRa, then it will be saved faster. And if you are saving the fine tune model, which will be saving this whole 5 billion parameters, then it will take time to save it.
Hmm. Yes.
Okay, then you can just give me, I mean, if any question, you can just write it on the Excel sheet. I will try to answer the questions. Okay.
Yeah. Okay. Thanks. Thanks a lot.
Thank you.